Hello, today we'll have our lecture about general physics, and this will be the last lecture that will be in midterm. I think it would be enough for these 6 lectures from 1 to 6, so this would be the lecture as I have divided the lecture number 6, and this would be the last lecture about mechanics. We had lectures about Newton laws, about motion, and mostly linear path. Then we had rotational motion, we had fluid mechanics. Now we will have the last lecture, and this is vibration, waves, and sound. So vibration or so-called oscillation, synonym. So oscillation or vibration, waves, it is the oscillation or vibration that travels in space, and the sound is probably the most common example of mechanical waves. So therefore we will consider sound in this lecture. So basically oscillation or vibration is probably you can describe in your by your own words. It is back and forth motion that repeats over and over again at regular time intervals. So basic example is just a simple pendulum. Pendulum is a mass, some kind of mass, probably imagine some kind of metal ball that it is attached to a string, and it can move if you pull it aside to this direction, so then it is in this position. You let it go, and then it goes from here, it goes to here, then it stops, and then it goes back again here. So and then it goes again to this position. And if there were no friction forces with the air and some kind of friction where it is hanging here somewhere, so then it would be, according to Galileo's law, that if there was no friction, so then it would move constantly. if there was no force to stop it. So it moves this, if this is point A, this is point B, this is point C. So it moves from, in our case, it moves it moves basically like this. So let's say it moves A to B to C, from A to B to C, then from C it moves to B to A, and it repeats. So this is the pendulum, or mass is just some kind of object which has mass and attached to a string. Another example would be some kind of mass. Mass that is attached, let's say it is some kind of object which has mass, and it is attached to a string. This is mass attached to a string. This is mass attached to a spring. Only one letter changes. See? Interesting. This is called the equilibrium position. Position B, where everything starts. Here, equilibrium position, if it oscillates from this equilibrium position to here, and it oscillates and goes here, and goes again to this position, and goes again back to this position. So here it would be also the equilibrium position for this spring example. So this moves due to two forces. Net force of these two forces, so it would be F gravity plus F tension. F tension of the string. This moves only one force. This would be F tension. This is horizontal motion. Gravity has no... Remember, in horizontal motion, the influence in horizontal motion, influence of gravity is zero. Horizontal motion, as you remember, because it is moving only in this, it has here the velocity has what is moving here and here. So velocity, acceleration, and this there's only Vx component. If we're talking about velocity, there is only Vx component. So gravity acts on Vy. No Vy component. Here it is motion in Vx and Vy. It's motion in x and y. No Vy component, only Vx. And here are two components, Vx and Vy components. So therefore we have gravity. I will explain later about this. Best example about this Vx and Vy was those throwing examples when we were speaking about thrown object to the horizon. When the object is thrown to the horizon, remember we had this kind of example when we throwing the ball to the horizon. So this is V, and it has two components. One is Vx and one component is Vy. So gravity only acts on Vy component. Therefore it matters when we throw the ball straight down or straight up, and here it also matters because there is a straight up component. Here there is no straight up or straight down component. Here it is, because part of this, there are two forces. One force is going down, another force is going to this direction. So one is going like this. This is gravity. One is going like this. The net force is the sum of these two, and this is the net force. So therefore it moves like this. This is F net. F gravity, F tension of the string. The same as we had the motion on the inclined plane. Similar example, except no friction here. And now parameters that characterize this oscillation. So there are parameters such as probably, okay, it would be three parameters. So one parameter is amplitude. So characteristics of oscillation. Characteristics. So amplitude. So amplitude is the distance at which the object is displaced from its equilibrium position. So if the object is equilibrium, it is here, ABC. It is the same pendulum. This is equilibrium position. It moves here, then it moves here, then it goes back from here, it moves there, then it goes from here, it goes here, then from there it goes there and back. So the amplitude would be, the distance would be here, this distance from here to here. It is the amplitude. Maximum displacement. Maximum displacement of object from equilibrium position. Frequency. Frequency, it is the number of oscillations per unit time. Amplitude is measured in meters. In meters, SI units. It can be millimeters, centimeters, and basically it is meter, the unit. frequency is measured in units per second. Units per second, how many oscillations occur per second. Units per second can be written as second to the -1, or it is hertz. So frequency, if you have, so frequency F would be number of oscillations divided by total time. Let's say you had 10 oscillations. In 5 seconds, so would be one oscillation, two oscillations in 1 second. It would be only 2 hertz. 2 hertz. Period would be time necessary for complete oscillation to occur. So units are seconds because it's time. So time is, this period is inversely proportional to frequency. 1 divided by frequency. Basically this can be described that it is total time divided by number of oscillations. Reversed. So this indicates the reverse. All right, now another thing would be the resonance. Resonance is the tendency of a system to vibrate at some frequencies to a greater amplitude. Means that if you have a tuning fork, let's say there is a tuning fork, it is a metal instrument which creates sound. Let's say you hit it with something and it creates sound. So it creates sound of a particular frequency called a pitch. It is constant frequency, let's say 1 kilohertz. It creates sound of particular frequency. So if you have this one and you have another one here with the same parameters, so because of this vibration, it creates waves, and these waves, they go to this and they make this tuning fork also vibrate, because this particular frequency corresponds to this. It has also the same frequency, that because they are the same tuning fork. So this has this vibrates on particular frequency. This also vibrates on this frequency. So this is called the resonant frequency, at which this tuning fork will also vibrate. So the resonant frequencies of this and this, they are the same. If you had different tuning forks somewhere here and it would produce 2 kilohertz frequency, this would not vibrate. So because this frequencies corresponds to the characteristics of this tuning fork, and also its composition and this in geometric characteristics. So another one example would be there is an example in slides when the bridge was broken. The bridge was there was a bridge, imagine, and the bridge was broken because of the wind. So it had some kind of resonant frequency, this bridge, let's imagine, and it had resonant frequency, and when the wind was on the same there were waves of the wind that were oscillating in the same frequency that the bridge had. So then the oscillation amplitude increased, the bridge started to vibrate, and then it collapsed. It's similar example when soldiers walk through the bridge and they move in constant pattern, and they constant pattern with some kind of frequency, and those frequencies of the bridge and soldiers movement, they match, because there are a lot of soldiers, imagine an army, and the bridge may collapse also. So another example would be simple pendulum or swings. If there is a child on the, let's imagine primitive human being on the swings, and imagine that it is swinging and you push the child at particular frequency, then his child's amplitude increases and he goes back and forth as the pendulum that has increased amplitude. So like to this position. Now the restoring force of the oscillation, restoring force so the restoring force is basically given here. In this example, you see the gravity acts downward, F tension acts to this direction where the string is. It's produced by a string, and gravity is produced by earth. So the net force would be the sum of these two. So the net force would be I have written it determined according to the rule of rectangle of vector as a vector, so the sum of these two vectors. So this would be the net force or the restoring force. So it is pulled aside. This pendulum is pulled aside, and then because of tension and gravity, there is restoring force, and so this pendulum moves to this equilibrium position. Because of inertia, it passes to this. It passes the equilibrium position. Then the restoring force starts to develop again here, because of tension and because of gravity. It starts to develop while it is swinging here, and it acts in the opposite direction. So then it develops here. Here it reaches its max, and then it makes this mass go back, and then it repeats back and forth. So this is this F net, this is F tension again, this is F gravity. So this is F net is the restoring force, F net, F restoring. So here the restoring force is produced by gravity and tension. Here the restoring force is only tension, because you move this mass attached to a spring to the right, let it go, then it moves here, then it goes back again there, and there the similar thing here, but there's only restoring forces, only tension, F tension here. Now it tells you that on your nodes that you have tells you that F restoring here it can be expressed as Kx if we have here x-axis. So this F restoring would be proportional. It is determined experimentally that F restoring force, it is proportional to the length of the spring. So the displacement of a spring from its equilibrium. So as if you pull the spring to this side, then your, let's say this is equilibrium position. So from this equilibrium position, let's say you pull the spring by 2 centimeters, it would be 0.2 meters, and K can be let's say 5 newtons per meter. So then F restoring force would be 1 Newton. So this is just example. So that because by experimentally it has been determined that this restoring force is proportional to the distance that it is displaced from that this object is displaced from its equilibrium position. So equilibrium position would be here, and then this coefficient K can be found by experiment measuring. You can find this example in the slides how it is done, but basically it is Hooke's law. Now, what else that it is important? So the restoring force we just talked, we can put plus. So oscillation or vibration is characterized by oscillations equation. So it is so if you have, let's say, something is oscillating back and forth. So if it's oscillating like this, and now imagine what happens if I move this paper to the left. See what happens? It's a very nice graph. Very nice graph. We can draw a line here and write that it is time. It is time, seconds, let's see. Here again, if it moves like this, if it moves like this, if it moves like this, if its oscillation is like this, I could move it, increase it to up, this paper up. So again, we got the same thing as you see. Oscillation here, oscillation here. So oscillation is how it is defined. It is defined as a sine or cosine function. So it is xt. This is xt in y-axis. This is position. It's defined. X is defined for position, so it can be yt defined if you want. Let's write maybe yt here. It would be easier for you. Yt, and it would be ya sine omega t, and it would be ya sine 2 pi f. So this omega is 2 pi f, and this is t missing. So this would be sine or sine. It can be sine or cosine equation. So this is the amplitude. Ey is amplitude. So Ey is here. And this is minus ya. Ya, ya here is also ya, capital A. Let's write capital A. Here is capital A, can be written here ya minus ya. So here is the period, time necessary for complete oscillation to occur. Complete oscillation occurs from here to here, from 0 to 0, goes to plus amplitude to minus amplitude, goes back to 0 to plus amplitude, minus amplitude, back to 0, 2t. Here is 3t. So if you, this omega is angular frequency. Angular frequency, and omega can be described as 2 pi f, where f is this regular frequency that we knew. Regular frequency. Oscillations per second. This equation basically comes from motion. If we expand the time axis, so what would we get? We would get like something like this. And what is this? This is, what is this? This is a circle. This is half of a circle. Half of a circle, half of a circle, again half of a circle, half of a circle. So one complete oscillation is like circle, like circle. So because oscillation, as you see, has the graph, this would be, if we expanded the t-axis, this would be this. So the graph of oscillation, this, is the same as a graph of an object moving in circle. We have an object here and it moves in circle. So it has the pattern of position yt like this. It goes half circle here to this position, stops, so it means here, it is this position, and then goes another half circle here. So it is sine, cosine equations. They describe oscillation because oscillation is the same motion as motion of an object in circle. So you can Google this. It is given in the course of, it's basically explained in the in high school. You might have missed, but you can Google it if you're interested in this thing. So oscillation is described in the same equations as motion, as circular motion. So this angular frequency comes from this kind of motion because there is no angle if you just thought about oscillation. Angle comes down when you try to this angular frequency. So some kind of angle here, phi, comes only when we try to describe it, we define with mathematics. And this angular frequency, it is the same as we described we were talking about rotational motion. It would be angular velocity or angular speed, because the units of it would be radians per second. Radian is a unit of angle, not degree, but radian in SI is SI unit for angle. This is, you can learn by yourselves because it's a bit different topic, but just for curiosity. Okay, now another thing. So this is another thing would be waves. Waves. So this oscillation that travels through space. So it can be, let's write two examples: empty space, or let's say mass, some kind of matter. So in empty space, what travels? So electromagnetic field, so electromagnetic wave here. So electromagnetic wave here, write EM, electromagnetic wave. Electromagnetic wave. Or through matter travels mechanical wave. Mechanical waves. This topic is for will be later discussed with electricity and magnetism. This through matter travels mechanical wave, so it needs particles to be transmitted, to travel. To travel, it needs particles to be present. So it means that in order the oscillation to be transmitted through space, through matter, it needs particles to be present there. As you know, sound, there is no sound if there is no air. So basically, the most common example is sound. In vacuum there is no sound. Sound can be transmitted through air, through water, through solids. So basically, sound wave is density or pressure disturbance that travels through, let's say, air, liquid, solids. So it's sufficient explanation. So mechanical waves propagate because of elastic properties of this. Elastic, it means that it is elastic, can be squeezed, then it presses. If you squeeze it, it can expand. So elastic, because of elastic properties. If you squeeze and then it expands. If you expand, then it squeezes. So let's say if you expand it, maybe it retracts then, let's say. So compressible media. So the speed of sound, it depends on the density of matter. It depends on pressure. It depends because pressure depends, also depends on temperature. Speed of a wave on a string, it depends on tension and linear mass density. You don't need to know this, but just know that speed of sound depends on whether it's air, liquid, or solid. In air, it would be 340 meters per second. In water, it would be 1,500 meters per second. In solids, let's say copper, would be 5,000 meters per second. So you can know that on the matter, means on density, on the properties of the medium, such as density, also depends on temperature, on ambient pressure. So waves transfer energy but not matter. Waves transfer energy but not matter. So they do not transfer matter. So waves can be, this is the systematics, let's say. Systematics, probably it's not very important for you if you understand, basically. So waves can be produced in, let's say, a wave on a string. If a string is fixed here to some kind of wall, so the wave can be produced. It could be a single pulse, or it can be multiple pulses. Let's say like this. It can be no time between time between pulses. It can be time between pulses. So here there is no time between two pulses. This is one pulse. This is some kind of, so from here to here it is one pulse. This is some kind of delay, small delay. Some lag time, probably not delay, but lag time. Second pulse. This would be third pulse. So the waves can be transverse and transverse and longitudinal waves. So transverse wave. So in a transverse wave, particles move in a transverse direction to the compared to the direction of the wave. So here would be the example, wave on a string would be an example of transverse wave, because wave travels to this direction and the string moves up and down. String moves up and down, and wave travels to this direction and back to this direction. So you see these directions, they don't correspond. So transverse would be wave on a string. Longitudinal wave would be the example of sound wave. If you have a speaker, that is producing compressions, so this would be compression of sound molecules. It produces disturbance in pressure or density. So sound wave, it is transmitted through the air as compression of air molecules. This would be compression, and this would be rarefaction. This would be again compression. This would be rarefaction, compression, rarefaction, compression, this again compression, and so on. So sound wave travels to this direction, and particles, they oscillate to this direction also, to this direction and to this direction, back and forth, they jiggle back and forth. So these directions, they correspond, they are not 90 degrees, they are not in the 90 degrees separation. So sound wave, as I wrote in here, is longitudinal wave. So sound wave, this series of compressions and rarefactions let's say in air, for example, okay? The simplest example. So compression will be high density or pressure. Rarefaction would be low density or pressure. The simplest example in air, in gas. So vibrating membrane in the loudspeaker produces this sound. So wave, it is also characterized by wave is also characterized by this sine or cosine function. So when we have here compression, so we get the amplitude up. When we have the rarefaction, we get down. When we get compression, we get up, then down, then up, then down. So you see, this I tried to match this. I don't know how I'm succeeded. So this would be to this would be this, here and here. So you see, and this would be to this. So compressions are rarefactions. So it would be, let's say, density here, density or pressure. So compressions are rarefactions, okay? This should be the same depth. Okay, so let's make a distance here. Distance. Meters, let's say. So this would be the wave equation. When it is written in distance, shown in distance, it says that it travels in the distance. It also, we can represent it in time, because then we would say how we would watch how if it was time, so so it means that, so when it is distance, so it means at constant time. If would be here time, so it would be at constant distance. So at some particular distance, we would see how the molecules vibrate, oscillate. And so basically the two representations of this sound wave. One, it is that it is in time at constant position. One would be in let's write here not distance but position. Position would be better. Here would be position at constant time. Constant time. So there would be 0, 0. This would be yt. This would y position x, yx. And this would also be oscillating. So in time we have period here, t period. Here we have 2t, 2 periods. Here we have amplitude EYA. Here we have minus EYA plus YA. So here we have period, the period of the oscillation. Here it is the same. Second period. So this would be if we have position here, then it's associated with distance. So here we would have lambda wavelength. Here we have 2 lambda. Sorry, 2 lambda. 2 lambda wavelength. 2 lambda. 2 wavelengths we have here. So here it is written like this is called peak, plus peak, here minus peak, let's say. When it is in distance, it is called I don't usually use these terms, but crest and throw. So it's again crest, throw. What else to mention? Again, equation is the same. Let's write it for yt. Equation is the same. It will be yt, ya amplitude. Yt, ya sine omega t plus coefficient and x. X means that it travels in both. It travels in space. It's associated with position. So x would be and it also it's two dependent two variables, t and x. Y dependent on t and x, travels in time and travels in space. So this means that it travels in time. Here, this means that it travels in space. The relation that is given between the period and the wavelength. So the relation it is that lambda is velocity of the wave or speed of the wave divided by frequency. Or it is, in other words, velocity of the wave times period. So as how I remember this, I remember from this, that lambda is Vt. Lambda is Vt because lambda is wavelength here. Lambda is wavelength. This is the speed of the wave. This is the period of the wave. So I remember by distance is speed times time, because period is measured in seconds, time is measured in seconds, velocity is measured in meters per second. It is the same. Lambda is measured in meters, so distance is measured in meters. So this is how I remember. And other there, it can be, since t is 1 divided by f, it can be written that t is 1 divided by f. So this is the relation, general relation. As you can see from here, oscillation is here, wavelength is here in temporal dimension, here wavelength is in distance dimension. So relation is this. It holds for any wave. Now there is something called wave interference. Wave interference. So wave interference. So if you have two waves, so let's say you have wave that looks like this and wave that looks like this. So as you can see, these waves correspond. The maximum peak values, they correspond. Minimum values, they correspond. So if you add these two waves together, the amplitude will increase twice. It should be twice, but imagine that this is twice. This is A, B, A plus B. This is called wave interference. When waves are in phase that means that peaks correspond, maximum places correspond, and minimum places correspond. Here minimum places correspond, maximum waves correspond, maximum places correspond. So then it is positive interference, constructive interference. Constructive, it means that we are constructing something, building. And there is also destructive interference when the waves are out of phase. So you can see this is minimum, this is maximum, this is minimum, this is maximum. This produces nothing. A plus B produces 0. They cancel each other out. This is minimum, this is maximum, cancel each other out. This is maximum, this is minimum, cancel each other out. This is maximum, this is minimum, cancel each other out. So this is destructive interference. So This applies to all waves. And one thing that I wanted to tell you is the last thing, that is musical instruments. You are not musicians, biologists. Sound wave is more important to you than musical instruments. Probably you know how sound is produced in human ear by receptors, or you can read it in your notes. So musical instruments. So musical instruments, let's say that they are, we think about stringed instruments that have strings, with strings. So the vibration of strings produces sound. So here what happens, that there are a lot of different instruments, let's say violin, viola, they are different sizes, guitar, and they have different sizes, so they have different length of strings. So short strings produce, if the string is short, let's say like this, it can vibrate like this, okay? The string is short, it can vibrate like this, so it would be short wavelength. If the wavelength is short, frequency is high. Frequency high, so wavelength is short, frequency is high, because lambda is v divided by f. So it means if this is short, if this is small, it has to be big if the speed is constant. Yes? And vice versa, long strings if the string is here, so what is the wavelength? The wavelength would be long. So wavelength long, this gives low frequency. Again, if this is big, this has to be small if speed is constant, because speed in air is constant, yes? V is constant in air, 340 meters per second, so it means that only frequency changes and wavelength. So violin and viola would produce different frequencies. Guitar and harp would produce also different frequencies. So that's why there are in the orchestra, there are a lot of musical instruments to overlap all the frequencies that are perceived by human ear. So therefore the string vibrates in different frequencies and produces different sound that we understand. Each string produces constant frequency, pitch. Why? Because it has because V is constant and lambda is constant. Lambda is constant, therefore f has to be constant. Two constants here, this also is constant. Because lambda is constant because it is length of a string. So one string of particular length produces one frequency. So, but there is a thing that musician is changing the, if there is a string, musician is fingering the string. It means that if we have a string that it is vibrating, let's say a string that it is vibrating, so musician is able to change lambda. Because lambda is dependent on the length of the string. Lambda is equal to the length of the string, let's say. But musician is and this is the length of the string, but musician is able to change length. I have never played any musical instrument. So it is but I imagine like this. So if you have played, it will be easier for you to understand. So it can change the length of the string, and therefore lambda. So one string produces more frequencies, but the length of a string changed. So therefore each string, let's write each string of particular constant length produces constant frequency. So because lambda is constant, but if musician changes the length of the string, it changes lambda, so then this string is yet another string. It became another string. So by grabbing here somewhere, it has changed L. By grabbing here, it has changed L. So it produces another number of different number of. It has produced a string with a different length. Let's say yes, lambda changed, frequency changed because V is constant. So and that's it. That there is about standing waves. That standing wave is a reflection of the wave. You probably, who wants, you can go deeper in these things. But basically, you have too much information here. So anytime you, if you understand this is just enough, because there are a lot of people who understand this, but they can say that something about standing waves, that it is reflection and that it occurs in musical instruments. But to know these things, it is much more important than to know the standing waves. That if you know this, you can go deeper, and then you'll see that the standing waves do something here, but this is more deeper. So this is just enough if you understand this thing. So it is a lot. So basically, we have finished the topics for a midterm part, and now if you have some questions, you can write me emails. I can write down all your questions, collect the questions, make another video. We can make some kind of live lecture. And if you have some problems by learning, also write me, and if there are some kind of unclean writings, because I'm writing here just a lot of things, so making mistakes, making difficult drawings, so you can contact me. I can explain something, or make or re-record some parts of the lecture. So let's collaborate, and you all have these probably all have these lecture notes. I also have them to follow the course, so I have these lecture notes and also have slides. So I would recommend you to take basic things from slides, because in slides there are a lot of examples, better information. So take the things from slides, read, learn them, then check here, because it is more expanded information than is given in slides in some parts. But slides have probably read slides and all this, and then listen to those lectures of mine that I have expanded a bit topics, because there are some good examples in slides, but those examples are poorly written here in the concepts. So just try to maybe read everything. Some better explanations are here, but good examples in slides, so some are connected. So read both of these and listen to the lectures, because in lectures I expand something, but in lectures I give a bit too much. So focus on the slides and concepts. If you know these things, you will pass everything fluently. So if you have questions, write me emails, and good luck.